A few weeks ago, while I was sitting there, just sipping it, something suddenly struck me. How does this bright orange, almost synthetic looking drink stay perfectly homogeneous year and year without even separating? I mean, think about that for a second. Any other liquid in that kind of state would eventually fall apart if you just let it sit. Muddy water, it clouds up, then drops sediment to the bottom. Oil and water, they don't even try to mix, separate instantly. Even if you try to fix muddy water using aluminum silicate, popularly called alum, it actually settles faster. So what kind of chemistry keeps Fanta looking exactly the same even after months of years of shelf? That question pulled me in, and I started thinking deeply about how Fanta is actually made. And this is where it gets interesting, because what looks simple is actually one of the most carefully engineered examples of modern food chemistry. So let's walk through it step by step. It all starts with water, not just any water, highly purified water, processed at controlled temperatures around 20 to 25 degrees Celsius through multiple filtration stages, softening, activated carbon, then final polishing. The goal? Absolute clarity. No ions, no particles, nothing that could interfere later. Now, here's where it all gets very cool. Next comes the sweetener, usually high fructose corn syrup or cane sugar, and this is dissolved completely into the water, forming what chemists call a true solution. Not a suspension, not a mixture, nor a colloid, just a solution, which means every single sugar molecule is eventually distributed at the molecular level of this substance. Nothing can settle, nothing can separate. Then comes the real flavor system, the final concentrate. This is where magic really happens. We've got orange flavor components, natural or artificial citric acid, preservatives like sodium benzoate, and brands like yellow 6 and red 40 that gives that significant orange look. And you'd never believe this. The pH is carefully adjusted to around 2.8 to 3.0, and that's very acidic. And it's not just for taste. That low pH actually helps stabilize everything, prevents microbial growth, keeps reaction under control, locks the system in place. Then everything gets blended in massive industrial tanks. Temperature, it is controlled between 15 to 25 degrees Celsius. Ratios, extremely precise, usually about 1 part syrup to 4 or 5 parts treated water. And this is where it gets even more interesting. Carbonation. Carbon dioxide gas is injected into the liquid under pressure, but not just any condition. The liquid is first chilled down to about 0 to 4 degrees Celsius. Why? Because colder liquids can hold more gas. Then CO2 is forced into the whole system at pressures between 15 to 80 psi. That's roughly 1 to 5.5 bars. The one factory setup, it stabilizes around 3.5 bars, and this gives you about 1.8 to 2.5 volumes of carbon dioxide. Just enough fizz, not too flat, not too aggressive, and finally it's bottled, sealed, quality checked, done, and you're ready to drink. What you end up with is not just a drink, it's a chemical stable system. Everything dissolved, everything balanced, nothing left to settle, and in theory, a sealed bottle of Fanta like this could sit for 100 years and still look the same. And that's when my curiosity took a sharp turn, because I started wondering, what happens if you break that balance? What if you introduce something aggressive, something that doesn't just mix, but reacts? That's when I reached out for bleach. Now, this wasn't your typical liquid bleach you found in your households. What I had was the solid form, calcium hypochlorite pellets. And the stuff is different. It's hygroscopic, which means it absorbs moisture from the air. Leave it exposed and it slowly turns into a thick paste, then hardens again. So what I had wasn't perfectly fresh. It had already reacted slightly with atmospheric moisture. And you will never believe this. That's actually made the experiment more realistic, because this is exactly how many people store it. You can even find similar products in stores like Walmart in the USA or local supply shops elsewhere in Europe or anywhere where you are. Now, before I even start, let's talk about what bleach actually does. Bleach is a powerful oxidizer. At home, it's used to kill bacteria, viruses, and fungi. It breaks down stains, destroys color molecules, sanitizes surfaces. In simple terms, it tears chemical structures apart. So now we have got a perfectly stable drink, which is the Fanta, and a chemical designed to destroy stability. And this is where it gets interesting. I started by weighing out 8 grams of the calcium hypochlorite pellets. Then I measured exactly 100 ml of distilled water. I added the pellets slowly. Now, normally you might expect some fizzing, which is okay, but because this had already absorbed moisture from the environment, where I said it's hygroscopic, so almost nothing happened. It just dissolved quietly, and that told me the reactivity has really dropped slightly. Next, I poured 250 ml of fresh Fanta into a 500 ml glass beaker. Bright orange, as you can see, fully carbonated. And the room temperature is about 28 degrees Celsius. And pH remains 2.8 to 3.0. Everything stable. Then I prepared a working bleach solution that I could use. I diluted it down to about 2.5% active strength. I measured exactly 20 ml and pulsed, because once this goes in, everything changes. So I added it slowly while stirring, and you will never believe this. Within 10 seconds, the color started breaking, not fading, breaking. The orange split apart, yellow streaks, swelling, collapsing, disappearing, and then came the bubbles. Not normal soda fizz. This was chemical gases being released. The acid in the Fanta reacting with hypochlorite, releasing chlorine-containing compounds. That sharp smell we perceived. About 30 seconds, the color loss accelerated. The dyes were being oxidized, literally destroyed at the molecular level, and after 2 minutes, almost no orange is left, just pale yellow and fawn. I let it sit 5 minutes, then 8 minutes, and this is where it gets crazy. It turned almost completely clear, like the drink had been erased. Same liquid, but chemically transformed. After 10 minutes, the reaction was basically done. No color, minimal fizz, slightly higher pH. Total breakdown of the original system. That's when it hit me. Fanta doesn't stay stable because it's strong. It stays stable because everything inside is balanced perfectly. But the moment you introduce something like bleach, that balance doesn't bend. It breaks, it shatters. And honestly, that's what makes chemistry so fascinating. One moment you got a drink that could sit unchanged for decades. The next, a simple reaction turns it into something completely different. So if you enjoy experiments like this, let me know what you want to see next. Stay random, stay safe, and as usual, subscribe for more chemical reactions. Thank you.